So let me start. So I just wanted to quickly review what happened. It looks like, I guess maybe the past 2 days all we've been doing is kind of repeating the same things to make sure they stay fresh in our minds. So I want to somehow draw the diagram with the most important objects, most important players that are related. So this is somehow supposed to indicate various series and coefficients that series and coefficients functors. And I will just draw it on the automorphic side. So A for short. And the point is that there are all these complicated stacks involved. So somehow making things rigorous is hard, but the idea is pretty simple and classical. So the idea is that we somehow try to identify automorphic forms, automorphic objects, using their Whittaker coefficients. And then we have to deal separately with zero coefficients and the non-zero coefficients. So the most fundamental, the most fundamental picture, so that's what's going on, is that we are studying the category of D modules on band G, which embeds into some kind of category of extended Whittaker coefficients. And when I say embed, well, this is more or less a theorem for GLN and conjectural for arbitrary G. And then we want to slice this into categories corresponding to different degeneration, to different degeneracy conditions on these Whittaker coefficients. And so there will be, the number of them depends on the rank of the group. So let me assume the simplest non-trivial case. So let me assume that G is GL2, in which case we have only two of those categories. There's the Whittaker category and the category, so that there are non-degenerate coefficients and the zero coefficients. And so on this level, maybe I shouldn't draw this arrow here. So this is not an action. So arrows are functors. So the formal relation between the categories can be expressed as follows. Now this bottom, this arrow on the bottom is some kind of a gluing functor. So it's a gluing. So we're thinking of this as something living on the open set. This is something living on the closed set, and then there's some kind of attaching information. So this is J. Formally, this is something like this. And the diagram, this lower triangle, is not supposed to commute. It only laxly commutes. So this exactly means that the category at the top is the gluing of the two categories on the bottom. And so this is all kind of understandable classically, except for the bottom arrow. So classically, we're saying something like automorphic forms can be understood using the Whittaker coefficients or Fourier coefficients, whatever you want to call them. Coefficients. And then we have it. If we want to completely identify the form, we have to consider all of them. But we can split this into two cases. So there are non-zero coefficients and the zero coefficient. And this, well, when I'm saying non-zero and zero, this refers to the index of the coefficient, not to the coefficient's value. So this is the somehow the key diagram on the automorphic side, and part of the project, and well, the subject of my talk last time, was to somehow construct a counterpart of this diagram on the Galois side. Okay, does it make sense? And so once again, the key idea is to identify objects using their Whittaker coefficients. So to construct two diagrams like this and then start just generating objects in both categories and making sure that their coefficients match. So if there are no questions, let me somehow continue moving around this diagram. Let me now just, because this it's easier to work with somehow the zero Whittaker coefficient and the non-zero Whittaker coefficients require different methods, so geometrically they're about different things. Somehow I really don't want to focus on the middle of this picture here. So this is again something classical. So let me just try to get rid of the middle here and see the relation between these three categories. And again, this is something that Dennis did yesterday. So let me call this kind of series and coefficients diagram. So I'm going to think of functors that produce an automorphic object, an object in D mod band G, as some kind of series, and a functor that takes object in D mod G and produces a D mod band G and produces something on the bottom row as a kind of coefficients. So now I only keep track of three categories. And want to know how these three categories are related. And if I just look at this, already in this diagram I have two functors. So these are the functors of the Whittaker coefficient that was denoted coef. So this is, let me actually maybe use a different color for names. So this is the non-degenerate Whittaker coefficient, and something that can be called the zero Whittaker coefficient, but the zeroth coefficient of the Fourier series is its constant term. So this is the constant term functor. So this is constant term. Yeah, I was worried that you got up and were about to say something scary. Anyway, so now the point is that both of those functors admit adjoints. So we have and we call those, so maybe somehow a more familiar one is this one, which I'm going to call the Eisenstein series. It's a mistake. So this is the Eisenstein series, and this functor is the Poincaré series, which we actually, I will use it sometimes, but maybe I still want to say that this, for us, this one is more important, essentially because we can use it to produce some very controllable generators in this, well, not generators, a bunch of things that almost generated. So somehow Eisenstein series are simpler than anything Caspidal or anything any Poincaré series. Okay, so and the adjunction relation between the functors is reflected on this diagram. So the one, if you care about these things, these are left adjoints, these are right adjoints, and so there's something being hidden. Well, there's quite a bit hidden between the lines here. And so one of those things is that, I mean, when we work with the modules, we don't have all 6 functors. We only have one set, one pullback that's always defined, one push forward that's always defined. That means that of the 2 adjoints, usually the right one will be easier to define. I mean, if not for infinities, that would be no problem at all. And the left one requires some justification. Nonetheless, the claim is that such a diagram exists. Okay, so any questions so far? Is this for what?
Arbitrary group.
Well, for arbitrary group, you will have more possibilities, but yes, the statement is that it's for arbitrary group. All right, now a couple of comments about this diagram. Again, maybe they are obvious, but might as well get them out of the way. Now, this thing here is a gluing. So this is a category. This behaves like a, I want to say a closed subcategory, a category of things supported on a closed set. This is the quotient by it. Now, this sequence is not in any way localization sequence, co-localization. It's not true that this category is somehow quotient of one by the other. So, and somehow we don't really have a way of, well, usually, like when you take most objects, they will have, well, maybe with one exception, you will expect that things will have some non-trivial images on both sides. So, for instance, if you start with an object here, apply Poincaré series, and then you compute the constant term, this is not supposed to be 0, and vice versa. So this is one comment. And the other comment is that I don't know if, maybe that's the least of your problem by now, but I don't know if you actually, anybody would object to me calling this functor the functor of Eisenstein series, because this notion of Eisenstein series has a, I mean, this is, there is some kind of more classical picture associated with Eisenstein series, and so I'm not sure to what extent it's clear that this is related. So let me maybe say a couple of words about this. So, I mean, this is, I'm calling it just usual Eisenstein series to simplify notation, but in a sense this is some kind of enhanced Eisenstein series. So maybe I should put some superscript on it, although I won't. So this is enhanced Eisenstein series in the following sense, that there's the usual one, the usual Eisenstein series is defined using the following diagram. So we can look at d modules on bun G, d modules on bun B, d modules on bun T, and, well, there are functors relate in these categories. So you can apply there are maps between natural maps between these stacks corresponding to morphisms of groups, and you can just do push-pull or pull-push. So just trace this diagram, and this is what somehow is maybe more familiar as the Eisenstein series. Well, it's, if I want to match it, I mean, it's not supposed to matter much. And here I would rather use, so this is what I, so this whole thing is normalized so that the constant term is somehow the usual one, and the Eisenstein series at first sight seems strange. So this is why I put Q upper star and P lower shriek here.
This Q upper star is not defined. That's
More than smooth. It's a smooth map.
So, well, you still, if you do it this way, you would have to explain why this makes sense. So why it's defined on the image of Q upper star. But this can be done. Okay, and so this is, so this formula for the usual Eisenstein series. So let me move this somewhere. So there's this usual Eisenstein series defined using Q upper star, P lower shriek. So we can somehow try comparing it with this with this enhanced Eisenstein series that starts from something really strange. It starts from this WGB, which is roughly speaking. So this is a functor from, let me just put, so this is the functor from d modules on bun T to d modules on bun G. And so roughly speaking, this, well, not this Eisenstein series, this enhanced Eisenstein series, but again, I will drop enhanced eventually. So it has the same target, but a different source. And I think Sam said it yesterday that somehow the meaning of this category is that it's supposed to be the best possible source of Eisenstein series. Now, first of all, why is this okay to still call this Eisenstein series? Well, roughly speaking, this source category is, so it's something like D modules on some crazy quotient, which is you start with a G bundle, then you reduce to a B bundle generically, and then you're allowed to mess this up by anything upper triangular. Should I be using this A or should I be using it? Anyway, so n over dels. So, and the idea is that somehow if you just look at closed points, this is indistinguishable from bond T, from the source of the usual Eisenstein series. But the points are glued together in a completely different, well, there are many more points glued together here. And so informally, I want to say that the idea of this category is that we look at this functor and we try to get as close as possible from bond T to bond G, so get our category, morphisms in our category, as close as possible to actual morphisms on bond G, but still keep some kind of T locality so that we can use our understanding of the geometric class field theory, so that to use our understanding of D modules on bond T to somehow describe this category. So this is the idea of Sam's talk. Well, I guess one way to interpret what he was saying is that that this category still admits some kind of description that is maybe it's not really local on T, but at least it's, I want to say that it's some upgrade, something extra to geometric class field theory. So this is somehow a version of bond T. So they have the same points, closed points, but they are glued very differently. And in very non-trivial way. In particular, even to understand what is written here, you have to develop a lot of machinery. Not here, to understand this category. All right, so this was maybe not very precise. Now, a precise statement, for example, one thing you can say is that one of those factors through the other. So this usual Eisenstein series can be obtained as a composition of something with the enhanced Eisenstein series. So, precise statement. So that this enhanced, sorry, the other way. So the usual Eisenstein series is the enhanced one, composed with, I don't really care. And moreover, that their images generate the same category in bond G. So if you want to make sense of words, the category, somehow the space of Eisenstein series inside the space of automorphic forms, it doesn't matter which one you use.
Why didn't you say what something is, because it's clarifying?
Sorry?
Why did you say that something in the box, what it is, because it's clarifying?
Well, because I didn't want to, I mean, you're supposed to just pull back from one to the other. And I think Sam wrote it last time, but I don't remember. I remember neither his notation, no. But, I mean, I feel that in order for this to make sense, I mean, it's pull back and then you have to induce things. So, I don't know. I'm not sure it would help. Anyway, so let me say that there are images of the two Eisenstein Eisenstein functors. Generate the same category in D modules of band G. So in other words, the category of Eisenstein series is unambiguous. And so, I mean, I'm not trying to somehow disrespect this usual Eisenstein series functor. I think that it fits very nicely into this picture. So the only reason why we focus on this one is to somehow minimize the number of objects involved. So for this reason, we somehow just focus on this diagram and just consider this Eisenstein series functor only. And the same can be said about the constant terms. Now, does it make sense? Now, somehow the idea is that very similar words can also be said on the Galois side. And well, since Galois side is superficially different from the automorphic side, the justification of the words will be different, but the diagram itself looks the same. And so this is the maybe a summary of what went on. Now, I don't know. I don't think I should try draw in the Galois picture now, but I can do it at the beginning of my talk. So maybe now is a good time to stop and ask for questions. Yes.
I wanted to make a comment that's not exactly in what you said, but it's I wanted to highlight the elements in the proof that simply do not exist in the number theory world.
Right.
Would it make sense to?
Well, I was about to say it, but it sort of fits better too.
Oh, you want to highlight them?
Go ahead.
No, no, no.
No, you should read it.
No, 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 no. Did you say that you wanted to highlight them?
Well,
Yes, please. It will be nice.
Yes.
so there is a point that I completely missed in Nick's talk 2 days ago, which I did here, but you explained to me yesterday. And
By the way, this is Yanis, for those who don't yet know.
so
Can I maybe say one sentence as a preface? Because so somehow I believe that the logic is that when we are dealing with Eisenstein series, it's mostly classical. Maybe there's a gluing functor, but it's somehow things make sense. There are maybe something advanced. So the difference is really that there is a way to deal with Caspidal story, and this is what this Oper and the Kazhdan-Lustig story is all about.
also another difference that I missed in Nick's talk 2 days ago was that you have this localization factor from quasi-coherent on what is it? On Loxis G to well, I guess the localization factor is the opposite, right?
Mm-hmm.
And I guess I should write horizontal jets on BG run, something like that, right? So, and you have the adjoint of this. So, this is something that we have in number theory, this adjoint. It is just, you take a Galois representation and you restrict it to the decomposition groups at each place. So it goes from global to local. But what you were able to show is that this is fully faithful, which in number theory is not the case in terms of Galois representations. Just the fact that two Galois representations are equivalent at every place does not mean that they're equivalent globally. Right? So this is a novelty of this.
I mean, for groups other than JLM.
for groups other than GLM. And this factor came from. Oh,
Too late. It's okay.
what can I erase?
Well, I think anything this, yes.
Okay, just. And this factor came from a map that I have no idea what it would mean in number theory, namely from some global object to some local object, space, I would say. And there is an analogous picture. So that's one of the things we cannot do in number theory. The other thing we cannot do is construct Caspidal representation. Yes.
I just wanted to say about this map that this map involves integration over the stack of local systems. It's taken of the quasi-coherent cohomologies over the stack of local systems. And it's even this, because this stack does not really, global stack does not really make sense as a, well, unless you're in characteristic 0, unless you're in this geometric setup. I think that this is somehow another way to look at why this map is a special feature.
Even in the Kac theory, it doesn't exist, at least at the moment.
Yes, it's not just difference between geometric and number theory. It's a difference between the RAM settings and yes. No, I mean the point is that, for example, at a single, supposed to be a representation at a single point. How do you describe it? Well, this representation, it's supposed to be a representation of G. So there's supposed to be a bunch of direct summons. So you need to know how many times each particular representation of G appears. So what you need to do, you need to take this representation. It defines a tautological vector bundle on log Cs, and you need to take the cohomology.
But that said, so although, okay, let me just elaborate more. So although, as Dim is saying, the function doesn't make sense, so it can't integrate over local systems, Vincent, his work, does something very, very close. We don't quite have that, but he kind of, his ansatz to classical Langlands in one direction uses something very close. He kind of exploits of this whatever he can. So it's it can be made more precise, but.
So we'll have a follow-up workshop on trying
Vincent?
to relate everything together.
No, we should have a workshop on Vincent separately.
So the other thing that we don't have in number theory is a way to construct from local data to construct automorphic data. And that came from the other part of the picture, which is this going to
Demote, rather.
yeah, so was there something around here maybe?
Bungee Deron.
Oh, you can, yeah.
And here also there are.
So
I copied it from some notes.
That's, no, I mean, it's more complicated, right? You have this as
So
well.
maybe it will.
so it's not budget.
It's
it's
geomod.
automorphic jets into VG completed at kind of
So
regular jets.
in Nick's talk yesterday there was there were factors written exactly like.
Yes, without the RAM, but
Then there's no
Without
doubt.
the RAM.
Correct as is.
So this is also something that we don't have, and it comes from, again, from a map of spaces, which is Bungee. Which I guess is the same.
well, I think on this level it's okay. So the problem is that we need, this is what Dennis was, and Nick was saying, that we don't really need quasi-coherent sheaves, so we need D modules actually, and you can, which means that here instead of looking at just jets on the formal disk, you also need jets on the puncture disk, and this is how the Kazhdan-Lusztig picture enters into play. And
what do you mean this is okay? I mean, this is again something that does not exist in number theory.
but what is the point is that, well, no, yeah, it doesn't exist in number theory, but it exists in, so this is not a, it exists in for L-adic things, because there is not an L-adic here. This is purely quasi-coherent. So,
Yeah, it's
yes, so
that exists over R. So that exists for arbitrary field. You don't need, there's no, because there's no D modules involved.
Okay, so
no, so I'm saying that yes, things become interesting here, but you need to make one more step when you start thinking about D modules, and then it also fails in fine characteristic, because here we're thinking of D modules as actual quasi-coherent sheaves with connections, and you cannot think this way about L-adic sheaves.
and you also made a comment that these are two parts of the same diagram in the quantum picture, right?
Yeah, so maybe I wanted to. So I was trying to answer Yuval's question, and so the point is that, let me just, well, let me enhance what Yanis has written. I'll write D mods, and here I have, instead of this, I'll have Kazhdan-Lusztig. So, I mean, it's some enhancement to put. So here it will be Kazhdan-Lusztig of Ron. So the point is that this picture and this picture are basically the same picture. So let's do it not for G check but for G. Then there exists a one parameter family that interpolates between the two. So it's what happens is the Kazhdan-Lusztig category degenerates to this. And what I was trying to emphasize in response to Yuval's question is that, so this category D of Bon-G, which we are kind of groomed to think about it as purely automorphic, in fact exhibits features of the Galois. So basically, in the geometric picture, both sides have the characteristics of both automorphic and Galois. Yes. Yeah, and basically the strategy of the proof is to kind of play one against the other. So that's kind of.
When you say there is a one parameter family, it's philosophical question or it's formal question?
No. Yeah, it's level kappa. No, you can just really.
You can do it.
Yeah.
As a real family, not as.
Yeah. Absolutely, over P1, absolutely. So, yeah, and that's. Yeah.
I wanted to remind everyone that this was actually mentioned, I think, on the very first day when somebody said that the two categories are essential of the same difficulty. That somehow on one side there's difficulty in D modules, and on the other side there's difficulty in local systems. So
yeah. So I mean.
The two sides are in some sense.
Yeah. So kind of this geometric picture exhibits more symmetry than the kind of the classical picture. Classical picture, automorphic is automorphic, Galois is Galois. Like you don't have Frobenius is on the automorphic side, and neither do you have the Whittaker model on the Galois. And today, my talk in a couple of minutes will be exactly the Whittaker model for Galois. Any more questions? So there will be opers in a couple of minutes. Yeah, by the way, so I want to quote an important lemma. So point A, point B, there exist sandwiches. So there will exist sandwiches. So the guy will bring sandwiches at, pardon? No, it's 11:30 he will bring the sandwiches. Yeah, so yeah. Okay, break.